Hi, I'm Raj Giridharagopal. I'm a senior research scientist at David Ginger's lab at the University of Washington. I'm going to discuss some of our work investigating time-resolved electrical microscopy of photoinduced charging and ion motion in layered perovskite materials. Many of us know about the conventional three-dimensional perovskite with the architecture shown at left with the formula AVX3. In fact, there are many symposia and talks at this conference discussing these materials. The prototypical three-dimensional perovskite is methylammonium lead triiodide. These materials offer a number of advantages for photovoltaics, and they exhibit very high power conversion efficiencies. One of the drawbacks of three-dimensional perovskites is that they tend to be somewhat unstable in terms of moisture, and so they break down in environmental conditions. This factor and drawback has prompted many researchers to turn to two-dimensional Ruddlesden-Popper type structures for these perovskites. The prototypical version of these is butyl ammonium lead iodide. In these materials, you have a layer of perovskite, and these layers are separated by a relatively bulky organic cation spacer. So in this case, a butyl ammonium cation is separating two lead iodide layers. These materials can exhibit high power conversion efficiencies in certain architectures, and they enable efficient light-emitted diodes. However, one of the interesting things about them is that they also tend to be more stable to moisture as compared to the three-dimensional counterparts. The reason being is that the organic cation spacer tends to resist moisture and be more hydrophobic. However, one of the interesting things about these materials is there's some debate about whether or not there's ion migration in these structures. So several groups, such as Jinsung Huang and more recently John Marone at Cornell, have published reports saying that there is very little ion migration in the n=1 version of these layered perovskite materials. This contrasts with some of the work looking at resistive memory type applications for these structures, where they did show that you can form ion filaments in these n=1 materials, which does imply that ion motion does occur. To sort of reconcile this debate, we turn to electrical scanning probe microscopy, particularly in the paradigm where we record and process multidimensional data. So what does this mean? This means that each individual pixel in the scanning probe microscopy image, we're not just recording the conventional topography where you get amplitude, height, and phase, we're also applying some time-dependent process. In this case, at each pixel, we're going to shine light on the photovoltaic material and then measure the response of the cantilever. We do that at each individual pixel, and this yields a large multi-dimensional data cube that we can then use post-processing algorithms on in order to extract some information. So in the context of this big data approach, what we analyze is butyl ammonium lead iodide films. These are n=1, where there's a single perovskite layer between these butyl ammonium cation spacers. We turn off the feedback and then digitize the cantilever dynamics and then process it after the fact. And we do this in one of two ways. The first is what's called general mode surface scanning Kelvin probe microscopy, or G-mode for short. And the second is fast-free, time-resolved electrostatic force microscopy, which allows us to measure force and gradient dynamics with microsecond to sub-microsecond resolution. In the first approach, this G-mode method, what we do is we bias the cantilever with an AC voltage, that is, we're not applying a voltage to shake piezo explicitly. Then we excite the system with light pulses, so we turn on an LED and shine light on the sample, and then measure the surface photovoltage response with respect to time. The way this is done is that at each individual pixel, we can extract a parabola of the deflection with respect to voltage. And then at wherever the vertex of this parabola intersects the x-axis, this x-axis being the voltage you are applying directly between the tip and the substrate, that corresponds to the contact potential. So this is an example of several of these contact potential versus time traces that you can measure using this technique. In this case, the contact potential is relatively flat, and then when we turn on the light, there's a sharp negative drop due to the surface photovoltage in these materials, and when we turn off the light, it relaxes back. One of the important things to note is that if we look at several traces all over the film at these locations marked at the top, you can notice in the graph at the bottom that there's a different time constant associated with each of these different spots on the film. The blue and the green tend to be relatively fast as compared to the red and the orange spots, where it's somewhat slower in order to actually evolve. So this implies that the contact potential has significant spatial variation in its time constant. This might be shown a little bit more clearly in this movie. So in this case, we're going to have a contact potential image at the top, shown at each individual time slice, and then where this white line is, we're mapping out the contact potential across that grain boundary. So where these dark lines are in the top are boundaries between the different crystals in these materials because it's a polycrystalline substrate. So in the red, this is going to be the normalized contact potential across that grain boundary, and then the bottom is the raw. So hopefully this plays. So the light is off currently. Once the light turns on, the contact potential shifts negative, so it becomes darker in the top image, as shown by the blue graph dipping down. More interestingly is if you look at the red curve, as this light turns on, there's a narrowing of the contact potential across this grain boundary, and then when the light turns off, it's going to widen, which is kind of an interesting and unexpected effect that the contact potential sort of smears out at this grain boundary over time. One of the other interesting issues is that there seems to be a time dependence to the photovoltage evolution at the grain boundary versus the neighboring pixels. And you can map this out more explicitly, is that at each pixel, we're going to actually measure the time constant for when the photovoltage is charging, and then when we turn off the light, so when it's discharging. So in this image here, we have the topography at the top, and then several contact potential images at different time slices. And then in F and G, what we have is the photovoltage charging time constant, where we fit a single exponential to the photovoltage charging. And then in G, we do the same but for when it's discharging. So what's interesting is if you look at the time constants, we're getting 250 to 600 microseconds or so for charging. And if you sort of do some back of the envelope calculations, you get mobilities on the order of 10 to the minus 5 centimeters squared per volt second, which is 100,000 times slower than would be expected for free carriers that are moving in these materials. So this implies that there is a slow dynamic process that occurs when you shine light on the BAPI film. And we attribute this potentially to ion motion or slow trap-mediated motion. The other interesting factor is if you look at the photovoltage charging maps in F and G, is that the interfaces tend to be slower because they have longer time constants, as opposed to the grain centers. To find sort of a second way to actually correlate this, we want to look at methods that can extract a slightly faster dynamic response in a different way. To do this, we do fast-free, time-resolved electrostatic force microscopy. It's kind of a mouthful in terms to say that, but what it does essentially is map out the cantilever frequency with respect to time at each pixel. So in this case, we are biasing the cantilever at each pixel, then we shine light and measure the raw cantilever response. And then using a demodulation method called the Hilbert transform, we can extract what's called the instantaneous frequency versus time. So that's the cantilever frequency as it evolves. So when the light turns on, the cantilever frequency will shift away from equilibrium and slowly relax back. Then finding the time it takes to shift farthest from equilibrium is effectively a proxy for the charging rate or the efficiency of that particular pixel. That yields pretty interesting maps as shown here. So the topography is shown at the top, and then in B we have the charging rate. So here what we have is wherever it's dark, that's a relatively faster pixel with time constants on the order of 85 microseconds or so. And at the grain boundaries, we have relatively slower time constants on 130 microseconds. If you contrast this with the frequency shift, which is something you might get in conventional electrostatic force microscopy, we see that there's a larger frequency shift at grain boundaries as opposed to grain centers. A larger frequency shift here means that there's more charge buildup. So what this means is that if you take these together, is that at grain centers you get less charge, but the charge that builds up is faster than at grain boundaries, where you have relatively more charge, or at least more EFM signal, and an EFM signal is relatively slow. To kind of reconcile these two things, we sort of turn to this cartoon diagram here. The hypothesis is that two effects are occurring. First is that there's light-generated photocarriers that diffuse in the surface potential. That leads to most of the surface photovoltage shift in these materials. The second factor that comes in is that near the interfaces and grain boundaries, halide vacancies are a larger portion of the mobile carrier population, leading to more net relaxation, but that does lead to slower overall dynamics as compared to grain centers. So this is kind of shown schematically in this top right image, where at grain centers, there's relatively little ion motion or slow trap-mediated motion as opposed to grain boundaries. What this does imply is that for BAPI materials or these layered materials in general, you want to try and optimize the grain boundaries in terms of reducing the amount of non-radiated recombination, or at least reducing the amount of traps and or the amount of deleterious ion motion that might occur. So with that, I'd like to acknowledge all of the people in our group, especially our collaborators at Oak Ridge National Lab that helped tremendously with a lot of this work. And thank you for listening.